Okay, so I sent you some information yesterday by email. So one of the information was the official web page of this subject. So yesterday I sent you the email with the official web page and with some informations about lectures and exercises. And I would start with the web page, more precisely with my personal web page. So you can see my personal web page on YouTube, but I don't know whether you can see the address. So the address is Math, as the Department of Mathematics, Feld, Faculty of Electrical Engineering in Davidse, cvut.cz, and my surname. And in the section teaching, you can see the web page or the link for the web pages of the subjects probability and statistics and mathematics for economy. In the syllabus, you can see, for example, the references, the literature, which I recommended you to study. But what should be enough for pass the exam is the page of the subject where you can find the slides of the presentations of these lectures I will give you. Then you can find exercises. I will talk about these exercises later when we will have exercises today. And you can see also some conditions for getting assessment and for the exam. But be careful, because nobody knows what will be tomorrow and in 1 month, in 3 months. So now the conditions for assessments are the same as it was in the last years. You should collect some points and you should write some tests. But I suppose that this year, when the teaching will be online till the end, you will have some homeworks instead of these tests. We will see, we will decide in 1 month. I'm sorry for that, but the situation is like you can see. So don't be afraid of getting the assessment. Maybe it will be only for homeworks. I suppose it will be only for some homeworks. So we don't have to talk about it now. It's too early. Now, if you don't have the questions about the organization of this subject, I would start with the first lecture. The first lecture will be from the beginning, from the basics of probability theory, which you probably know, but I will recall the basics for you, and I will use the notation which will be held during the whole semester. Okay, so the probability theory in so-called Kolmogorov sense starts with the term sigma algebra. The definition is quite complicated from a mathematical point of view, or it can look quite complicated for you, but you don't have to be afraid of it, because I will explain it on an easy example. What does it mean? So imagine that we throw a classical die with 6 sides, and on the first side you have 1 spot, on the second side you have 2 spots, and so on. Then, in fact, it is a trial, it is a random trial. And in this random trial, we can get 1 of 6 different results. The set of all possible results is denoted by Greek letter omega, has 6 elements, omega 1, omega 2, and so on, till omega 6, where omega 1 means there is one spot on the die. Omega 2 means that there are two spots on the die, and so on. Where omega 6 means that there are 6 spots on the die. This is the set of all possible results of the random trial I talked about, and these possible results are called elementary events. But there can be a situation, more general situation, where we don't care about the concrete result, about the concrete number of spots on the die, but we care, let's say, about an event that the number of spots on the die is odd. So imagine the event. Let's denote it A. The number of spots on the die is odd. Then, what does it mean that the number of spots on the die is odd? It means that the number of spots is either 1 or 3 or 5. So, in fact, A is a set of 3 events, omega 1, omega 3, omega 5. Yeah? In fact, we can interpret this event as the set of all possible elementary events in which the result of trial can fall. Yeah? So from which we can take the result of the trial in order to fill the condition that the number of spots on the die is odd. And this point of view, when we look at the elementary events and the events as to be set, then these events consisting of some elementary events are in fact the subsets of this omega of the set of all elementary events. Therefore, we make a structure which is called sigma algebra, as is written on the slide. And it is nothing than the set of usually all subsets of the set omega. So, why do I write usually all? It is natural to consider all subsets. In order, we can consider such events like the number of sets is odd. For example, B, the number of spots is less or equal to 2, and some other events. But when we consider some concrete situation, let's say we have a game, if we threw the die and the number of spots is odd, I will pay you the beer. If the number of spots is even, then you will pay the beer for me. Yeah, so in the case when we consider only the odd or the even number of spots, we can have the sigma algebra, which is not so dense. We don't need to have the subsets of the type of the even B. Yeah, so it can be enough to have only A and some even, let's say, C, the number of spots is even, and that's all. Yeah? So theoretically, it can be enough to have only these two events in the set of subsets, but usually, because we want to make some more general models and to calculate the probabilities of more general situations, usually we consider the set of all subsets of this capital omega, and the elements which are usually denoted by capital letters starting from A are called random events. Yeah? So that's the term of sigma algebra. It is the set of all subsets of these elementary events. These elements are called the events, and on these events we will define the probability. Are there any questions to the term sigma algebra? If not, let's define the probability and the term probability space. So in the literature, you can find more definitions of probability. Usually, the probability is defined as a function on this sigma algebra A, so as a function on the random events. And it is the function whose values are taken in the interval from 0 to 1. The definition is usually given by 3 properties, and there are many other properties which follow from the definition. I decided for the definition in the sense that the probability is, as I said, a real function on the sigma algebra A, satisfying these 3 conditions. The probability of the whole omega is equal to 1. And practically it makes sense, because what does it mean when we are asking for the probability of the whole omega? We are asking for the probability that the result of the random trial will be from the set of all elementary events. But because it is the set of all elementary events, it means that one of these results must happen. So then the probability that one of these all elementary events will happen, will be the result of the trial, must be equal to 1. It is sure. On the other side, the probability of empty set is 0. Why? Because the probability that nothing of these elementary events will happen is 0. Some of these elementary events must happen. Some of these elementary events must be the result of the trial. Yeah? So therefore, the probability that the result will be in empty set is 0. It cannot happen. Yeah? So that's the first property which defines the probability. The second probability is that, sorry, it should be better to write here that the probability of an event is greater or equal, not greater than 0. Yeah? But the information was that the probability cannot be negative. Yeah? So the probability will be always positive, or in some special cases it can be equal to 0, but it cannot be negative. So when you calculate some exam and you will make some mistake and the probability will be in your calculations equal to -2 or -7, you know that there is a mistake. Probability cannot be negative, of course. And the third property which defines the probability is that when we have the sequence of disjoint events means that they are disjoint in the set point of view. So it means that there is no intersection in the set of the elementary events which defined these events. When we have the sequence of all these events, then the probability of their union can be calculated as the probability, as the sum of the probabilities of the events. So for example, when we consider our events here, then here we have the event A. Here we have the event C, and the probability of the union of A and C is calculated as the probability of A plus the probability of C. And, okay, we didn't speak about the concrete values, yeah, but in fact, this union is the whole set, the set of all elementary events, so the probability should be equal to 1, and indeed, the probability of getting the odd number on the die is naturally equal to 1/2. We will talk about it later. The probability of an even number on the die is 1/2. So the probability of the whole omega is really equal to 1. Yeah, but it holds more general. When we have, for example, the even D, which means there are exactly 2 spots on the die. So it means, in fact, that D it corresponds to the elementary even omega 2. Then the probability of A union, the probability of the union of A and D is equal to probability of A plus the probability of D. It makes sense. The probability of A union with D is the probability of having the result in one of these 4 elementary events. So in fact, it is the probability that one of these 4 events happen, and because we have the total number of 6 events, naturally, as you know, the probability, you expect that the probability is equal to 4/6. The probability of an odd number is 1/2, and the probability of getting exactly 2 spots on the die is naturally 1/6, because we have 6 events and only one of them satisfied that there are 2 spots on the die. So it is okay. But be careful. This is possible only in the case when these events are disjoint, when they have no, when they have empty intersection. When we consider, for example, the events A and B is that there are at most 2 spots on the die. So this is the even B. Then we cannot calculate the probability of their union as the sum of their probabilities, because in this case we would calculate the probability of omega-1 twice. Okay? But I start to talk about the properties, but first I should give you the definition. Yeah, so what I wanted to say is that the definition of the probability is given by the 3 conditions, but the conditions are very natural. The conditions are, in fact, as you know them from some basics of probability you probably had at secondary grammar schools, and in general, which you had before. So this was the definition of the probability itself, and usually we consider in some situations for which we want to build some model, the whole triple, the set of all elementary events, the set of their subsets, and the probability defined on the subsets. This triple is called the probability space, and it is not so important term for practical uses, but all theorems we will have here will start with let's have a probability space. And so just in order you know what it means. In fact, it means that we know the situation. We know all elementary events which can occur. We know which events can be built from these elementary events, and we know the probabilities of some concrete events. That's the situation which is called the probability space. So let's continue. We will use the following terminology for the events, situations which I described before. And the terminology is, so first, as we said in the definition, the probability of empty set is equal to 0, and it means that in fact it is impossible that this event occurs. So therefore the empty set is called impossible event. We won't use this term very often. The probability of the whole omega, the probability of all elementary events, meaning that the result will be in the set of all elementary events, is equal to 1. And we call it sure event because it is sure that one of the elementary events will happen. So therefore it is called a sure event. These two terms are not so important, as I said. What is more important is the union of two events. The union of two events is really the union as we understand it in the set theory, as I said before. So when I again draw the situation, here we have the event A, I'll try to use some colors. So, for example, orange color, we will have the event B. Event C, that the number of spots on the die is even, is given by red color, and lila color will be used for D. And when we consider, for example, the union of A and B, as I said, it is the union as in the classical set theory. So it is the set of all events, of all elements, belonging either to A or to B. Now, again, we can write omega 1, but it is not necessary because omega 1 is already included in this union, so we add only omega 2, and that's it. What does it mean in the terminology of probability theory? It means that the result of the random trial will be in the set consisting of these 4 elements. And in fact, when you imagine what does it mean practically, it means that either the event A or the event B occurred. Yeah? So it means that when we consider the union of some random events, it means that either one or the second one or both of these events occurred. Analogously, we can consider the intersection. The intersection of A and B is the intersection of the sets A and B. A and B have the intersection consisting of only one element, omega 1, and it means, in fact, that both, it is the element belonging both to A and B. In probability terminology, it means that both A and B occurs. So there must occur both the events A and B together. It means that the number of spots is odd, and the number of spots is less or equal to 2. Yeah? Or better say, maybe we should start with the element B. Yeah? So the number of spots is less or equal to 2. And moreover, we need that it is odd. Then it must be omega 1, it must be the situation that there is one spot on the die and nothing else. Yeah, so really, indeed, the intersection and the unions are the intersection and the union, respectively, of the sets. But from the practical terminology, from the practical point of view, it means that in the first case, at least one of these events occurred, and in the intersection case, it means that both these events must occur. We can consider also the difference of the events. So the difference of the events B minus A is the set of all elements belonging to B which don't belong to A. So all elements from B not belonging to A is the only situation, only one elementary even omega 2. And practically it means that the difference of two events are the events which elementary events from B which occurs, but the event A cannot occur. Yeah, so the elements, the event B occurred, but the element A didn't occur. That's the practical meaning of the difference of the events. We can skip the terminology 6, that something is sub-event of B. I will talk about it later on the next slide. What is very important term in probability theory is the term of complement of the event. It is the complement of in the classical theory, set theory terminology. So the complement of A are the events which occurs when A didn't occur. So in our case, when A means that the number of spots is odd, then the complement is that the number of spots is even. So in fact, in our case, it is the even C. And it is very practical when we want to calculate the probability of A. Sometimes it is easier to calculate the probability of complement, and there will be some useful, very easy relation between these two probabilities you will see on the next slide. The 8 points. What does it mean that the events are disjoint? It is again corresponding to the terminology from set theory. The sets are disjoint when their intersection is empty, and the same situation is here. When the intersection of the sets of the events A and B is empty, we call the events disjoint, and practically it means that they cannot occur together, both together. So if one of these events occurred, you know that the second one couldn't occur and opposite. And the sequence of joint events, okay, we can skip the terminology now, 9, because we will talk about it later in more details. So this was the basic terminology, and now we will talk about some basic properties on the term which we define, which we mentioned. Okay, so let's go back to the properties. So the first property, which I repeated many times, the probability must be between 0 and 1. So your result of probability will be always between 0 and 1. If not, you know that you made some mistakes. So when you write the exam and you will calculate the probability and the result is 2.7, be careful. You don't have to calculate it again, but write me to the exam that you are aware of the fact that you made the mistake because the probability must be between 0 and 1. The second property. When you have two events and one of them is a sub-event of another, the probability cannot be greater than the probability of the larger one. Why? Because each probability, the probability of each elementary event is positive, or it cannot be negative. So when we have the probability, let's say, of the event A, and we want to calculate the probability of A union B, so the probability of something what is bigger than the event A, it is the probability of A plus the probabilities of the remaining elementary events. And the probabilities of the remaining elementary events cannot be negative. So the probability of the larger event must be larger or equal to the probability of the smaller event. So only be careful when you calculate the probabilities of some sub-event, of some event and its sub-event. The probability of the sub-event must be less or equal to the probability of the event itself. The third property is a very important property in probability theory, because very often, as I said, it's easier to calculate the probability of complement. But what holds for the complement and the event itself? The event, together with its complement, give us the set of all elementary events. So it means that the probability of this union is equal to the probability of the whole omega. The probability of the whole omega is equal to 1, and the event A and its complement are disjoint events. So the probability of their union can be calculated as the sum of their probabilities. And it means that the probability of the event A can be calculated as 1 minus the probability of the complement. So in this situation, and the situation occurs very often, in the situation that it is easier to calculate the probability of the complement of an event, then it is very easy to calculate the probability of the event as 1 minus the probability of its complement. So it is very, very useful property. Okay, then the probability of the union. So, as I said, the probability of the union of disjoint events can be calculated as the sum of the probabilities of the concrete events. So, for example, when we calculate the probability of A union D, it can be calculated as the probability of A plus the probability of D, because the probability of A is again given by the sum of the probabilities of its elements, and when we add the set D, we add the probability of the elements of D. But when we want to calculate the probability of, let's say, the union of A and B, we cannot calculate it as the probability of A plus the probability of B, because in this case we would take the probability of all events of the set A, of the event A, and when we add the probabilities of all elementary events from the set from the event B, we would add the probability of the event omega 1 once more. So the way how to calculate the probability of the union of sets which are not disjoint is very easy. We can calculate the sum of probabilities of events A and events B, but we must subtract the probability of the events whose probabilities would be calculated twice. Yeah, so in our case, it is the probability of these 3 from the total number of 6 events, 3 over 6, plus the probability of B given by the probabilities of these events, 2 events from the total number of 6 means 2 over 6, but since the probability of the event omega 1 was calculated twice, we must subtract the probability of these events, and we get what we expect, the probability of these 4 events from the total number of 6 events, so 4 over 6. Yeah, so this is the way how to calculate the probability of a union in general when we have the general events A and B which are not necessarily disjoint. Okay, the property 5. Again, we consider one sub-event of another event, and there will be some situations when we need to calculate the probability of their difference. Now, for a while, let's forget our example with the die and imagine another situation. Let's say the temperature in a given moment in this class. So consider that we are looking for, or we are studying the random events corresponding to a given temperature, or to a temperature in a given moment in this class. For example, in 2 hours. Let's consider an even k that the concrete event, that the temperature is less than 20 Celsius degrees. Consider L, the event that the temperature is less or equal to 25 degrees. Now imagine the situation. Here, let's consider all elementary events which describe the concrete temperature. Here, we have our points from the events K and L. And suppose that we have some function, some model, describing the probability that the temperature is less or equal to A. This function really exists. It is called a distribution function. Sometimes also called cumulative distribution function. We will talk about this function later in more details, but just for beginning, for simplicity, imagine that we have a model describing the probability that the temperature is less or equal to each value A, and we care about the probability that the temperature is between 20 and 25 degrees. The probability that the temperature is between 20 and 25 degrees is given by the probabilities of all these events between 20 and 25. But we have only the function describing the probability that the temperature is less or equal to some A. What can we do? We can calculate the probability that the temperature is between 20 and 25 degrees as the probability that the temperature is less or equal to 25, which is the probability of all these elementary events, minus the probability of all these events. Yeah? So when we take the probability of all these events, meaning that the temperature is less or equal to 25 degrees, and we subtract the probabilities of all these events, meaning that the temperature is less or equal to 20 degrees, we get the probability of all these events, meaning that the temperature is between 20 and 25 degrees. Yeah? So in fact, we calculate the probability of the event L minus K, and it can be calculated as the probability of L minus the probability of K. And now, when we have the distribution function, it is nothing than the distribution function in the value 25 minus the distribution function in the value 20, but we will talk about this distribution function later, as I said. So now I wanted to show you when it is useful to have this information that the probability of difference of the events can be calculated as the difference of their probabilities. And the last property. The last property says that when we have some disjoint events a sequence or set of disjoint events. No, sorry. The number, it was in definition. So here, the number 6 says that when we have the set of disjoint events whose union gives us the set omega, the set of all elementary events, then the probability of the union is in fact the probability of the set omega. So it is equal to 1, of course, but the information is in the first equality that the probability of such a union can be calculated as the sum of the probabilities of the events. We will see later. We can skip the details of these properties because we will talk about it in each situation separately. So, are there any questions to these basics of terminology, basics of probability properties, and so on? Okay, if not, then I will continue with some special probability spaces. So in fact, it means some special situations which you can consider when you make some model. The first probability space is a classical probability space, which is, for example, the situation in our first example when we threw the die, because in this situation we have 6 elementary events. Each of these events has the probability 1/6, because when we have 6 events, the probability that arbitrary of it happens is 1/6. In general, when we have some m events, some finite number m of the elementary events, then the probability of each event is equal to 1/m. We consider the sigma algebra, the set of all random events which can happen, which can be combined from these elementary events, to be the system of all subsets of the set omega, and the probability of the random event A is calculated as the number of events corresponding to the event A over the number of total events. So for example, when we calculated the probability of the event A that the number of spots is odd, we calculated it as 3/6 because there were 3 odd numbers, and the total number of numbers was 6, so 3/6, 1/2 was the probability that the number of spots will be odd. The probability that the number of spots is less or equal to 2 was again calculated as the probability of 2 events, or as 2/6, because there were 2 events satisfying the condition that the number of spots is less or equal to 2 from all 6 possible events. But the life is not so easy. So it can happen that there are some complications. The first complication is that the number of events is not necessarily finite. For example, when I mention the temperature is in fact continuous. So when we consider the continuous continuous domain of elementary events, then we cannot calculate the probability as the number of events corresponding to A over the number of all events, because the number of all events as well as the number of events corresponding to the event A is infinite, and it is uncountably infinite. So in this case, we must consider something else. Instead of the numbers, we will consider some geometrical characteristics, and the geometrical characteristics depends, of course, on the dimension in which we are. So in general, the probability, the number of elementary events is given by as a subset of RD. And usually, because usually when we draw a picture and it is very difficult to draw a 4-dimensional picture or 5-dimensional picture, yeah, so usually it is useful in the dimensions not so high, let's say in dimensions 1, 2, or at most 3. Then the set of all random events is given by so-called Borel sigma algebra on the set of all elementary events. If you don't know the term Borel sigma algebra, you can imagine it as, again, as the set of all subsets which you can construct from this set omega. Yeah, there are some special mathematical properties of this sigma algebra, but it is not important for our subject. So you can imagine it as the set of all subsets, which you can imagine to construct. And then the probability of a random event A is given by the ratio of so-called d-dimensional Lebesgue measures. Probably you don't know what Lebesgue measure is, but it is nothing than the volume in the corresponding dimension. So it means that when we consider one-dimensional space, the Lebesgue measure of an object is the Lebesgue measure of a line segment, and it is the length of the line segment. So in one-dimensional space, the Lebesgue measure of a line segment is the length of the line segment. In two-dimensional space, it is the area of the set, and in three-dimensional set, it is volume of the three-dimensional object. And we can generalize it in higher dimensions, but as I said, the aim is to draw the picture and to derive the result, the probability from the picture, so it makes no sense to talk about higher dimensions. We will stay in these 3 dimensions, and I will show you an example. How to use it. So, example, I think it's example 3. There is a large garden whose sides are 40 meters times 100 meters, and there is a dog running in the garden. Let's say that the orientation of the garden is such that here is the north, here is the south, here is the west, here is the east. The question is, what is the probability that the dog is in a given moment closer to the south side or border of the garden closer than to the remaining sides or borders. So it means, what is the probability that the dog is in some region where is in a point which is closer to the south side, then to the east side, then to the north side, then to the west side. And because we know that the set of all elementary events, the set of all positions for the dog is continuous, we cannot calculate the probability as the number of events corresponding to the situation over the number of all events, but we must use this geometrical probability. First, what we need is to define the region where the points are closer to the south border than to the remaining borders. It is quite natural to form the line between the north and the south borders. Yeah, so all points which are in the upper rectangle are closer to the north border. The points from the lower rectangle are closer to the south border. But what is the line, what is the border between the points closer to the south and closer to the west? It is, in fact, the line where the angle of the line with the horizontal line is 45 degrees. Yeah, it is, in fact, the x of the angle. And the same situation is on the right side. Again, we construct a line where the angle between the line and the vertical or the horizontal, it is in fact equal. Line is 45 degrees. And in this way, we get the region corresponding to the points which are closer to the south than to other directions. We need to calculate the area of this region, and there are several ways how to calculate the area of this region. Let's call this even to be the even M. So we will calculate the region M, and it can be calculated, let's say, as the sum of areas of this triangle, and this rectangle. So the area of M is, when we have 40 degrees, here it means that half of 40 meters. Here it means that half of this length is equal to 20 meters. When we have 45 degrees angle here, the same angle is here. It means that here we have the same length, 20 meters, and analogous situation is here. Again, we have 20 meters here. So the remaining length is equal to 60 meters. So it means that the area is the rectangle, the area of the left triangle, which is 20 times 20 over 2. Left triangle plus 60 times 20, it is the area of the rectangle, plus 20 times 20 over 2, which is the area of the right triangle. So the total area is 200 plus 1,200 plus 200, 1,600 square meters. The area corresponding to the region of all elementary events is the area of the whole garden. It is 4,000 square meters, and it means that the probability of the dog being closer to the south border than to the remaining borders is the ratio of the area of M over the area of the garden, which is 1,600 over 4,000. So it is 0.4. Is it clear? Or are there any questions? Okay, if not, then believe me that the life can be more complicated than I showed you. And the complication, the next complication is such that the probability of the elementary events, or the probabilities of elementary events, are not necessarily equal. So, let's consider a situation when we observe the number of children of randomly chosen woman and in this situation we have the set of elementary events given by omega 0, omega 1, omega 2, and so on, where omega I means that the woman has I children. Yeah? So omega 0 means that the woman has no child. Omega 1 means that the woman has one child. Omega 2 means that the woman has two children, and so on and so on. But the probabilities of the elementary events are not the same. It is natural to imagine that the probability of having two children is much higher than the probability of having, I don't know, 20 children. It can happen theoretically. Of course, it cannot go to infinity from biological reasons. But theoretically, there is no reason when we consider the woman has 25 children not to have 26, from a mathematical point of view. But you know, naturally, that the probability of 20 children is much lower than the probability of, let's say, 2 children. So what can we do in this case? We must have some model for the number of children, or we can estimate the probabilities. So let's say that the probability of 0 children is equal to 0.05. The probability of 1 child is equal to 0.1. The probability of 2 children is equal to 0.4. The probability of 3 children is 0.15. The probability of 4 children is 0.1, and so on. The only rule is that the sum of all these probabilities must be equal to 1. And how we calculate the probabilities of random events, which consist of these elementary events, we just make a sum of the probabilities of the corresponding elementary events. So, for example, when we care about the probability that the woman has at most 2 children, then we calculate this probability as the probability that the woman has no child plus the probability that the woman has 1 child plus the probability that the woman has 2 children. And we can calculate it as the sum of these probabilities because these elementary events are disjoint. One woman cannot have together 0 children and 2 children. Either she has 2 children, or she has 0 children, or she has another number of children, but she cannot have 0 children and 2 children together. So these elementary events are disjoint, and the probability is equal to 0.05 plus 0.1 plus 0.4, which is 0.25. That's it. I'm sorry, just a few seconds. O půl třetí. 5 minut a končím. Jo, děkuji. So, that's the probability space, which is discrete, as well as the space concerning the number of spots on the die, but the probability of elementary events are not the same. And the last situation is the general continuous probability space, where we mix both these complications together. First, we consider the uncountably infinite number of elementary events, and moreover, the probabilities of these events are not the same. So let's go back to the example with the temperature. So theoretically, when we imagine the temperature, theoretically it can happen that here is minus 20 degrees, or that here is 40 degrees. But the probability of these extreme temperatures is very low, while the probability of the temperature somewhere around 20, let's say 23 degrees is higher. So we use a function describing the distribution of the temperature, and when we want to calculate the probability that the temperature is in given interval A and B, let's say as before between 20 and 25 degrees, we calculate the area below this function. And while the area between 20 and 25 degrees is very high, then when we take another interval of the length 5, let's say between 30 and 35 degrees, is much lower. So for this purposes, we use this function describing the distribution of probability. The function is called density, or more precise, probability density function. And because it describes the total probability, its property is that the integral, which is in fact the area below this function, the integral from minus infinity to plus infinity must be equal to 1, because the probability that here is some temperature from minus infinity to plus infinity degrees must be equal to 1. Some temperature must be measured in this class. So it is the case when we have uncountable infinite number of events and their probabilities are not the same. Are there any questions? Okay, so if not, we will meet in half an hour, let's say around 3, on the second channel, which I sent you in email, and we will have some exercises. We can solve some questions to this lecture, and if you have some other questions for organization, we will solve it on the exercise too. So thank you for your attention, and see you in 40 minutes on the second channel.